the red subscribe button right under the video and also the bell icon to get notification on any of our latest updates on the videos.
Hello friends, you are once again welcome to Smart View Kids Tutorials. Today we are going to continue our lesson in Sudden Mechanics 2. We are going to solve the B part, and before we proceed, we have already derived the equation of point load acting on a simply supported beam in the A part. So to continue the question, we are going to solve the second part, which says the maximum deflection of such a simply supported beam of length 3 meters is 4.3 millimeters when carrying load of 200 kilonewtons at its midspan position. What would be the deflection at the free end of a cantilever of the same material as A, length and cross-section, if it carries a load of 100 kilonewtons at a point 1.3 meters from the free end? Okay, we are going to proceed. So we have we have the B part, and in the B part we would first derive the equation for the bending moment of a cantilever beam fixed at one end and free at the other. Supposing we have something like this, and we have a section XX somewhere a distance x from the free end, and the cantilever beam has a total length of L. We have a point load acting at the free end W, where x is equal to 0. Now, before we start anything, we know our bending moment equation and the shear forces are important. So our shear force at section XX would be equal to negative W, because it acts downwards. Then our bending moment, which is the force times the distance of displacement, bending moment at section XX is equal to negative W times X. Now our equation for the bending moment M at XX is equal to the modulus of elasticity times the inertia, the moment of area, multiplied by the second derivative of the slope, making d squared y dx squared the subject of the formula. We have that mxx over ei, and on substituting the value of m, we have negative wx over ei. So therefore, integrating the above expression once, we get dy dx to be equal to 1 all over ei times negative wx squared over 2 plus a, which is a constant, and we already established that a is always a constant, and due to an indefinite integral we have its value. So And we already knew dy dx to be our change in slope equation. So this is change in slope. Change in deflection or slope. Now we integrate this very expression here further, and it yields us with y, which is our deflection, is equal to 1 all over ei into negative wx cubed over 6 plus the integral of a constant is what? X, right? So plus another constant b. So this is the expression for our deflection. Next, what we are going to do is we put in the boundary conditions given, and we have that boundary conditions right at x is equal to 0. We have that y is equal to y max, and this very expression will come at the end. And also at x equal to L, what do we have? At x equal to L, that is x increases from the right at this point, from the left towards the right. So at the point where x, from this point where the beam is freely supported to the point where it is fixed, that is this distance L. At such place, we have our deflection y to be equal to 0. Therefore, y is equal to 0. So when we substitute the value in this very equation, we have that y, which is equal to 1 over ei into negative wx cubed over 6 plus ax plus b. So we are already told that x is equal to 0 at this point. So, right. So therefore, we have that 0 is equal to 1 all over ei multiplied by negative wl cubed now over 6 plus al plus b. We have two constants here, but we can substitute the next condition to get the value of b or a. Therefore, at x is equal to L, the change in deflection would be equal to 0, and our equation says dy dx is equal to 1 all over ei times negative wx squared over 2 plus a. But since x is equal to L, it implies that 0 is equal to 1 all over ei into negative wl squared over 2 plus a. From here we see that a is equal to wl squared over 2 multiplied by ei. So having gotten the value of a, we can now get the value of b. So therefore from this equation we have already established that 0 is equal to 1 over ei into negative wl cubed over 6 plus the value of a now is wl squared times another l, that is this l, divided by 2ei plus b. So we can make b the subject. We have that b is equal to 1 over ei into, sorry, we have b to be equal to negative wl cubed over 2ei my plus wl cubed over 6. So therefore we have this expression, and on solving we would get negative 3wl cubed plus wl cubed over 6ei, and finally we get the value of b to be equal to negative wl cubed over 3ei. Now we substitute the value of b here and a into the expression of our deflection y. So we have y to be equal to 1 all over ei into negative wx cubed over 6 plus the value of a was gotten to be wl squared ei right over here. So we have um, w l squared over 2ei, right? Then minus w, this should be x, there should be an x here, minus b wl cubed over 3ei, right? Right. The next thing we are going to do is we'll substitute our boundary conditions. And for the first case, we'll consider where x is equal to L, our y would be equal to 0. So therefore, substituting inside this equation, we have that y, which is equal to 1 over ei into negative wx cubed over 6 plus ax plus b. It implies that y is 0 and would be left with 1 over ei times negative wl cubed over 6 plus al plus b. But unfortunately for us, we have two constants. How are we going to do about that? It's simple. We substitute the next condition at x equal to L. The change in the deflection dy dx would likewise be 0. So therefore, bringing down the equation of change in deflection, we know that dy dx equal to 1 over ei times negative w, x here is L, so we'd have negative wl squared over 2 plus a, right? So we can easily say that 0 is equal to 1 over ei times negative wl squared over 2 plus a, and finally we get a to be equal to positive WL squared over 2. Substituting the value of A in this first equation, we can be able to get the value of B. So therefore, we have that 0 is equal to 1 over EI into negative WL cubed over 6 plus, now the value of A is found to be WL squared times L over 2 plus B. Now B would then be equal to WL cubed over 6 minus WL cubed over 3. Solving this would arrive with the fact that negative 2 WL cubed over 6 is equal to negative WL cubed over 3. So finally, we have that our constants A is equal to WL squared over 2 and the other B is equal to negative WL cubed over 3. So our equation now becomes y is equal to 1 all over EI into negative WX cubed over 6 plus our value of A, WL squared over 2 times X, right? Then minus B, which is WL cubed over 3. This can be rewritten as 1 all over EI into negative WX cubed over 6 plus WL squared X over 2 minus WL cubed over 3. With this, we can now be able to find the maximum slope, that is when y is equal to y max. We have that x should be equal to 0, right? And it implies that from the equation above here, we have y max is equal to 1 all over EI times WX is 0, WL squared X is 0 likewise, would only now be left with negative WL cubed over 3. So therefore our maximum deflection Y max is equal to negative WL cubed over 3EI, right? To solve the question, let's refer back. We have that it says the B part, the maximum deflection of such a simply supported beam, that is the first beam we have here, simply supported beam of length 3 meters is 4.3. This implies that the maximum deflection Y max would be equal to 4.3 millimeters, which is the same thing as 4.3 times 10 power negative 3 meters. And it says it has a length of L 3 meters when carrying a load W of 200 kilonewtons. W is 200 kilonewtons. We have W equal to 200 kilonewtons, which is the same thing as 200 times 10 power 3 newtons, right? So given these values, when we refer back to our maximum deflection equation here, we are to determine the values of EI. So therefore, from this very point here, we have 4.3, which is our maximum deflection, times 10 power negative 3 to be equal to 1 all over EI into our W is said to be 200 times 10 power 3, and it has a negative sense, times our L cubed, which is 3 meters. We have 3 meters L cubed, all divided by 48, and making our EI subject of the formula, we would have negative 200 times 10 power 3 times 27 over 48 times 4.3 raised to the power of negative 3, and finally is equal to 26.2 times 10 raised to the power of 6. Right. Next, what we should do is we refer back to the question again to know the remaining part. And it asked, what would be the deflection at the free end of a cantilever of the same material as A? That is, it has the same material as the free simply supported beam. Length and cross-sectional area are all the same, but here it should carry a load of 100 kilonewtons at a point 1.3 meters from the free end. Now it implies that our W in this case would be 100 kilonewtons and our X would be 1.3. Our length is still 3 meters as before. So we have already established that the maximum deflection, the Y max, to be equal to negative WL cubed over 3EI, right? So what is the value of Y max? It's simple. We have that Y max is equal to negative 100 times 10 power 3 in this case, times our L, which is 3 meters cubed, over 3 times the value of our EI here is 26.2 times 10 power 6, and when we calculate we get our value to be 8 point. The question says what would be the deflection at the end of the cantilever of the same material as the simply supported beam with same length and cross-sectional area if it carries a load W 100 kilonewtons at a point 1.3. So therefore in this case our X would be equal to 1.3 meters, our L is still 3 meters, and our W now would be 100 kilonewtons. So we are to get the value of Y, which is the slope. We have 1 all over EI into negative WX cubed over 6 plus WL squared X over 2 minus WL cubed over 3. So having our values, we have 1 over 26.2 times 10 power 6 which is our EI, minus 100 times 10 power 3 multiplied by 1.3 cubed divided by 6 plus 100 times 10 power 3 multiplied by our L is 3 and it would be squared times 1.3 all divided by 2, then plus minus 100 times 10 power 3 multiplied by 3 raised to the power of 3 divided by 3. Now, when you calculate the above values, you would end up with the value of the deflection to be equal to 8.51 times 10 raised to the power of -7 meters. So now we are done with the question. Hopefully you enjoyed the video and we'll meet next in another course. Thank you very much.